Hello everyone. I hope you're doing well. Today we have another discussion and it's about two-dimensional finite element method. Unlike to the other videos, we only will discuss about the theory part. We will derive the big form of the PDE. We will discuss about the Neumann boundary conditions, Dirichlet boundary conditions, and mixed boundary conditions. And the code related to this discussion, I put it in my Telegram channel. The link of the Telegram channel exists in the description of this video. You can find it there and download it from there. If you think everything is okay after this video and you can make connection between theory and the code, everything is fine. But if you think you need more practice, we can have another video and discuss about the code. So for now, let's start the theory part. Okay, we have Poisson equation and we are trying to solve this partial differential equation over this rectangular geometry with well-known boundary conditions, and we have in the Dirichlet boundary condition the value of the potential is known at the upper boundary, lower boundary, left boundary, and right boundary. We know that this Laplacian in two dimension is like following, and I can rewrite this equation like this. And here we assume that the f function right hand side is a constant value. If this function is hold, I think we can easily conclude that by multiplication of both hands out of this function with a general function of psi, its relation also should be holds. And we know that in a calculation of a PDE using finite element, we need to discretize the domain into some finite element. And here I used triangular element, and let's assume that the area of this triangle is defined with omega and the boundary is defined with gamma. And I want to integrate both hand side of this equation over the area of such an element, and the A is here is the element of the area. And for simplifying this equation, I want to calculate these terms, and we know that we can write this term like the derivative of psi with respect to the x times to the derivative of v with respect to the psi plus psi second derivative of v with respect to the x. And you see that we can replace this term here, with this equation simply. Therefore, we can have the same, we can derive the same relation for this term. And by substituting of this term with such a terms, we can have these equations. And now, a bit rewriting, we have area integral and another area integral, and again the right hand side. And if we look at this equation, we can simplify it more by using of Green theorems. And Green theorem says that indeed, area integral of divergence of any vector quantity is equal to the overall flux of that vector from the boundary of the domain that is surrounded the desired domain. And if I use the Green theorem, I can simply show that this area integral can be replaced with such a line integral. And this line integral is over closed contour, and we have the same term and the same term of the right hand side. And I just send this term to the right hand side of the equation. And we know that we should solve such a using a finite element method. For each element, we have some number of nodes. In using of a linear shape functions, we have 3 nodes for any triangular element. Therefore, we need to solve such an equation for all the nodes, and we know that we need to define some shape function at each nodes. And when we define 3 shape function, noticing that we have 3 nodes, we know that the numerical solution is approximation of the analytical one, and this approximation is linear combination of some coefficient at the nodes times to the shape functions that we defined for each node. Therefore, we need to solve this equation for all of the nodes. And for a typical node with I, we have such an equation, and I just substitute this linear combination of the shape function and the coefficient into V here and here. Yeah, therefore we have a same equation for any typical nodes or for any typical shape function psi I, but I did not substitute potential to be linear combination of potential. We will discuss about this integral later, and we will see why. Therefore, this is the let's say this is the weak form of the Poisson equation, by assuming that we are using triangular shape function, and we are going to triangular element, and we are going to use linear shape function. Therefore, it will be the weak form representation of the Poisson equation. And as I mentioned, we need to solve this equation for all nodes, and each node has a shape function. I recommend you to first watch the previous videos. It was the same topic but in one dimension. Therefore, I think that watching that video will help you to understand this video better. Therefore, now that we have three nodes, three shape function, we wrote this previous equation for all three shape functions: psi 1, yeah, psi 2 here and here, and psi 3. Now we have a system of equations, and we saw that we can easily just simplify it in notation. We can write the same system of equation like this. And again, we can write this system of equation in a matrix representation like this, where in this definition the element of this matrix is integration over area of the element times to the derivative of psi I psi j with respect to the x plus the derivative of psi I with respect to the y times to the derivative of psi j with respect to the y, and this is the element of the area. And the s vector is defined to integration over area of the elements of which function, shape function, times to the right hand side function, and this is the same boundary integral that we found using the Green theorem. Imagine we have a typical let's say triangular mesh. We know the position of x, we know the position of each nodes, and here, for example, for node number 1 we have x1 y1, for node number 2 we have x2 y2, for node number 3 we have x3 and y3. But it is convenient for our calculation, for ourselves, to, let's say, map this triangle over some other coordinate. We call this coordinate let's say natural coordinate, yeah. And we do this mapping in a way that the map of the node number 1 is located at the origin of this new coordinate. The map of node number 2 is located at the 1 and 0 of this new coordinate, and the node number 3 is located at 0, 1. And this natural coordinate is zeta, eta. Yeah. Now we are trying to use some shape function in this natural coordinate, and we know that we define some properties for the shape function, and the property is following that each shape function, yeah, should be 1 at one node, and it should be 0 at the all other nodes. Therefore, if we try to use some linear shape function, a possible linear combination in this coordinate will be c1 plus c2 zeta plus c3 eta. Yeah. And as I mentioned, at node number 2, that eta and zeta both are 0, this shape function should be 1. Yeah. Therefore, putting 0 here, 0 here, we have c1, and we say that this shape function we want it to be 1. Yeah. Therefore, we can immediately get 1 for the c1. At the node number 2 here, that zeta is 1 and eta is 0, this shape function psi1 should be 0. Therefore, putting 0 here, c1 that we found is 1, and the zeta is 1 and eta is 0, we get minus 1 for the c2. And at the node number 3, that zeta is 0 and eta is 1, the shape function again should be 0. here should be 0. This is 1. We found C2 to be minus 1, but here zeta is 0, therefore this term is 0, and plus C3, again we get minus 1 for the third coefficient, therefore this is the first shape function. Yeah. Again, second shape function could be linear combination in this new, let's say linear shape function in this new coordinate using the same properties. Yeah, this shape function number 2 should be 0 here and 1 here. Therefore, when it must be 0 here, C1 should be 0. At this node, the shape function should be 1. Putting 1 here, 0 that we found, C2 times to the 1 plus 0, C2 will be 1. And at this point, this shape function again should be 0. Therefore, we get 0 for the third shape function and for the third coefficient. Therefore, the second shape function should be just putting this coefficient here. We can see that the second shape function is just zeta. And using the same properties at the different nodes, yeah, we can easily show that the third shape function should be eta. Yeah. Just using the same condition that third shape function should be 0 here and should be 1 here. We can calculate this coefficient. C3 will be 1, and this 2c, this C1 and C2 will be 0. Therefore, the third shape function will be eta. An interesting thing about this shape function, we can see that the psi2 and psi3 are independent because in this coordinate these axes are perpendicular to each other. Therefore, psi2 and psi1 are independent, but psi1 is a linear combination of psi2 and psi3, and you can see that this relation holds for the three shape function, that sum of three shape function is always 1, because if you substitute psi2 here, yeah, zeta that is psi2 here and eta that is psi3 here, and bring it to the left hand side, you can easily show this relation is hold. And this is the geometrical representation of the three shape function psi1, psi2, psi3, and you see that we are dealing with some let's say plane, and the value of this plane is 1 at the origin of this coordinate, or at the origin of node number 1 it is 0 at the position of node number 2, and this is again 0 at the position of node number 3, and you can see here psi2 is only 1 here, and psi3 is only 1 here, and here is 0, and here is 0. We say that okay, as we can find the potential to be a linear combination of the shape function with some coefficient in the same manner, we can say that x coordinate and y coordinate can be also a linear combination of three shape function, and that x1, x2, x3, y1, y2, and y3 are the coordinate of the node number 1, 2, 3 in xy coordinate. Yeah, and if I substitute psi1, psi2, and psi3 from what we found to this equation, we get these two equations. Yeah, and after simplifying, gathering the common term, that here we have zeta here, and eta here, we get such an equation, and we define this x2 minus x1 with x2 1 bar, x3 minus x1 with x3 bar, and y2 minus y1 with y2 1 bar, and y3 minus y1 with y3 1 bar. Yeah, therefore this is the relation between let's say the mapping equation from the xy coordinate to the eta zeta coordinate, and we have indeed the coordinate of each nodes, that is x1 y1, x2 y2, and x3 y3, and we see how they are connected to each other. Therefore the same equations. Yeah, now that we calculate the shape function, it's time to calculate the matrix element from the weak form that we derived. Yeah, and this is what we found for the matrix element of M. Yeah, but this is indeed written in xy coordinate, and if we want to calculate this matrix, first of all, this shape function derivative of shape function that is that is a function of x and y, we should transform it to the function of eta and zeta. Also, we need to transform xy to the new coordinate of eta and zeta. Okay, just recalling again the shape function that we derived. We can write the derivative of psi with respect to the zeta with the chain rule of differentiation, and it means that the derivative of psi with respect to the zeta is derivative of psi with respect to the x times to the derivative of x with respect to the zeta plus derivative of psi with respect to the y times to the derivative of y with respect to the zeta. Yeah, and we can write the same for the derivative of psi with respect to the eta. And we see that we can again write this system of equation in a matrix representation. And I call this matrix with J, that stands for Jacobian. And you can calculate this Jacobian from this equation that we derive, because we need derivative of x with respect to the zeta. X with respect to the zeta is x to 1 bar. Yes, here. Y with respect to the zeta, it is with respect to the zeta, it is y to 1 bar. Yeah. X with respect to the eta, it is x31 bar, and y with respect to the eta, it is y31 bar. Okay. And now, because we are interested to write derivative of shape function, that is with respect to the x, as a function of derivative of shape function with respect to the zeta, all we need is to calculate the inverse of this Jacobian. And once we calculate the inverse of this Jacobian, this derivative of psi with respect to the x and y will be a function of derivative of psi with respect to the zeta and eta. Yeah. Therefore, and how we can calculate the inverse of this matrix, I think you know, it is 1 over determinant of J, and the rule is that we change this element and we multiply this element with -1. Yeah. And this is the inverse of the Jacobian matrix. But interesting thing about the determinant of this matrix is that you know how to calculate the determinant of this matrix. It is nothing, just this multiplication minus this multiplication. Yeah. And if we substitute x21 here, I just recall that this x21, y31, and y21 and x31 indeed are some constant number that shows the difference between x of each nodes and y of each nodes. And if I substitute x21, y31 here, and y21 here, and y31 here, based on what we define, and after a bit rearranging, you can get this equation. And this is a familiar equation that gives us the area of a triangle. This is when we have a coordinate of a triangle, this is 2 times of the area of triangle. Or in other words, strictly speaking, determinant of the Jacobian matrix is always 2 times of area of element. Okay, and this is what we said about the writing of the derivative with respect to the x and y as a function of derivative with respect to the zeta and eta, and we calculate this Jacobian. And we can now, because we have the function as a function of eta and zeta, we can calculate this derivative. For example, for psi1, derivative of psi1 with respect to the zeta, it is -1, and with respect to the eta, it is again -1. And I just substitute derivative here. And after multiplication, we can get these terms. This multiplication to this multiplication gives us this term, and this multiplication to this gives us this term. And again, if we simplify this, because this is y3 minus y1 plus y2 minus y1, because we have a minus here and a plus minus here, therefore we have minus y1, and here we have plus y1, and here we have minus y1. After cancelling y1 and minus y1, we get y23, and the same for this term, because this is x3 minus x1 minus x2 minus x1. Minus x1 plus x1 will cancel each other, and we get x32. Therefore, Now we have an explicit value for derivative of psi with respect to the x and derivative of psi 1 with respect to the y. That is some let's say constant number, because area of element is constant, and the difference between the coordinate, we know the difference between the coordinate of the each node. And in the same form, you can easily show that derivative of psi 2 with respect to the x and with respect to the y has such a relation. And also you can easily calculate derivative of psi 3 with respect to the x and psi 3 with respect to the y. That is again some constant number. Now that we calculated this derivative of psi with respect to the x as a function of derivative of psi with respect to the zeta, now it's time to substitute here. But we calculated this in new coordinate, but also we need to calculate integral not in xy coordinate but in eta and zeta coordinate. There's an equation that says if we have a function in some old coordinate and we map this function to some other coordinate, any double integral is in new coordinate should be let's say can be calculated like this function in new coordinate times to the Jacobian, and this Jacobian we calculated it. That gives us from we calculate the Jacobian from the mapping equation. Let's say from the mapping equations, times to the d zeta d eta. And this equation is attributed to a German mathematician, Carl Gustav Jacob Jacobi. Therefore, we will use this formula without proof. And I'm just recall that what we found for psi 1, for derivative of psi 1 with respect to the x and y here. Therefore, if I want to calculate m11, it will be psi 1, psi 1, psi 1, psi 1. And we substitute from here in this equation, and all this term are constant. They can go out of the integral, and this is very simple double integral, and also 2a is a constant. And if you calculate this double integral, you see that m11 should have such a relation, and we see that this m11 is a function of area of the element and the coordinate of the element. You remember in one dimension when we derived the matrix, it was a function of length of element, because we were in one dimension. Therefore, somehow we can say that in one dimension area of element is length, in two dimension area is area, and in three dimension this matrix should be a function of volume. We can show it. And if you calculate the other terms, just by substituting of what we derived for psi 1, psi 2, psi 3, in this equation, and you can derive all of the element of this matrix, and you see that this matrix is symmetrical, because this term is equal to this term is equal to this term, and this term is equal to this term. You can show it easily. Now we can calculate psi I again. We have SI, we can calculate SI, but because this integral is in xy coordinate, we need to transform it to the new coordinate using the same formula of the Jacobi. And in new coordinate, because f is a constant, it goes out. We have 2a that comes from the Jacobian, and if we substitute psi, that is a function of eta and zeta in this integral, and calculate in double integral, we can get S1, S2, and S3 to be f times to the a over 3, very simply. Therefore, this is the S vector. This is the S vector, and this is some unit vector times to the some constant. It's a function of right hand side and the area of element. Now we calculated the M, we calculated the S. Now it's time to calculate the integral boundary. For the integral boundary, we know that we need to calculate all of this M, S, and integral boundary for all of the elements. Now imagine that we have such a domain that is discretized using triangular mesh like this, and here I just highlighted two neighboring mesh, E1 and E2, and separated it to show that what should be the value of this boundary integral when we try to calculate for the internal boundary. What I mean by internal boundary, I mean that we are trying to calculate this boundary integral only for the boundaries that are at the, let's say, inner, at the inside of the simulation domain, not at the border of the simulation domain. And if you look, you can see that the unit vector of this line segment and the unit vector of this line segment is the same, but because the direction is different, they are opposite to each other. It means that this unit vector, it should be minus of this unit vector. And you can easily see that if this is nx, this is for nx of element 1, this is nx of element 2, again they are opposite to each other. And if this is ny of element number 1, yeah, and this is ny of element number 2, again they are opposite to each other, therefore they are related with to each other with -1, like this. Yeah. Now we are trying to calculate the boundary integral has 3 terms, b1, b2, b3. It means that for any integral we need to calculate for all nodes. Let's try to calculate the boundary integral for the element 1 and the node number 1. It means that we need to calculate from let's say counter from 1 to 2, yeah, and it will be psi1 times to the derivative of v with respect to the x times to the nx e1, yeah, plus psi1 of element 1 times to the derivative of v with respect to the y times to the normal vector, that is ny of e1. And if we write the same boundary integral for the second element, we have such an equation. And what is different here is that we have here nx e2 and ny e2, and we see that nx e2 and a1 e2 are minus nx e1 and minus ny e1 respectively. It means that if we substitute nx2 and nx1 from these equations here, we get a minus, and if we try to sum this to integral, it will be what? It will be 0. Why? Because every term is the same. Every term here, nx1, but with some negative, therefore it will be plus. ny1, nye1 and n1e2 is the same, some plus. And the shape function in this node is the same, because indeed this node number 1 for this element and node number 1 for this element is one node actually, and they are identical. And when we try to calculate the integral, for example, over this path, we know that psi1 is 1 here and goes 0 at this node. Again, for this element number 1, psi1 of element number 2, psi1 of element number 2 is 1 and then goes here to the 0. Therefore, we have identical shape function over this path for element number 1 and element number 2. And for example, if again we try to calculate the contribution of node number 2 on the b vector from the element 1, it will be like this, and node number 3 from element 2, it will be like this. Again, if we substitute the normal vector from this relation, negative is appear here, and it will be plus, and these two terms will cancel each other. You may ask, wow, why shape function of the element number 1 at this node and shape function of element number 2 at this node is identical? Because these nodes are identical first, then when we calculate the integral from this path to this path, or from this, let's say, this node to this node over this counter, yeah, again we have a shape function that is 1 and goes 0 here, and we have a shape function that is 1 and goes 0 here, and this shape function are identical. Therefore, this b2 and b3, when we sum them up, they will cancel each other and the result will be 0. What I want to conclude? I want to conclude that in derivation of the weak form of partial differential equation, we achieved some boundary integral using the Green theorem. Yeah, and we can easily see that the contribution of this boundary integral for all internal edges are 0, because these edges will be this, I mean the integral over these edges of this element and this element cancels each other. Integral over these edges of this element and this element cancels each other. Integral over these edges of this element and this element again cancel each other. But what about this element, for example? We see that we have some edges here that there is no element at the side of this element to cancel the boundary integral. It means that we need to calculate the boundary integral only for the edges that are coincide with the boundary of the simulation. Yeah, just keep it in your mind and do not try to calculate this boundary for all edges. Now that we know this fact, let's try to calculate this boundary integral only for the edges that are located on the boundary of the simulation. Yeah, I can just rewrite the same equation. I factor out this psi I. Yeah, and about the boundary conditions, we can have three famous boundary conditions. That is Dirichlet boundary condition. It means that we know the value of this this unknown, let's say unknown variable that we are trying to calculate. In Dirichlet boundary condition case, we know this unknown only at the boundaries, and we try to calculate inside the domain. And the Neumann boundary condition says that we do not know the value of this unknown variable at the boundaries, but we know the derivative of this unknown variable in the boundaries, and you know this is Neumann boundary condition. We can have mixed boundary condition, means that we may know the linear combination of Neumann and Dirichlet boundary condition, and as it comes from the name, it's mixture of Dirichlet and Neumann. Sometimes it is called a Robin boundary condition. And about this integral, when we are dealing with Dirichlet boundary condition, this integral even for the edges of the elements that are located at the boundary of the simulation is 0. Why? Because although we know the value of the function, but in this integral we are dealing with the derivative of function, and we do not have any information about the derivative of function. Therefore, in dealing with Dirichlet boundary condition, again this integral should be 0. But in the case of mixed boundary condition and the Neumann boundary condition, let's assume that the right hand side of a mixed boundary condition is some known value q, yeah, and when gamma is 0 we have mixed, and when gamma is non-zero we have Neumann boundary condition. Yeah, gamma is 0 Neumann, gamma is non-zero mixed. Okay, and in two dimension this divergence, indeed we can write this divergence like this. Yeah, and we can see that this term that we achieved here is appeared in this boundary integral. Means that if I rewrite this equation, I can write this term to be q minus gamma 1. Yeah, and if I substitute this term with q minus gamma 1 in this boundary integral, yeah, it means that now all I need to calculate the boundary integral only for the mixed or Neumann boundary condition, and I can find relation from the boundary condition to simplify this integral like this. When gamma is 0, yeah, q is some constant, we need to calculate this integral. This is Neumann boundary condition. When gamma is non-zero, again we have this relation, yeah, and v is some constant, gamma is some constant, and again we can calculate this integral. But for the case of Dirichlet boundary condition, this boundary integral is 0 for all edges of the triangle. Now you remember I say that I don't substitute this v to be linear combination of psi 1, because proving that this integral boundary integral at the internal boundary is 0 by having just v is more simple. That's why I keep it like v, not the linear combination of shape function, but this is time to substitute v to be the linear combination of the shape function as this. And if I use the expand form of this this sigma, I have this equivalent for the boundary integral. Now I can calculate B1, B2, B3 associated to the node number 1, number 2, and number 3. Imagine that we have such an element and the numbering is following, and this numbering is counterclockwise. I here should mention that you must number the nodes in a counterclockwise direction to avoid any negative number in calculation of the Jacobian. Therefore, we can have, for example, 1, 2, 3, 1, 2, 3, or 1, 2, 3 as we have here. And you see that now node number 1 and node number 3 are located on the boundary. It means that this edge in that is representing the boundary of our simulation. Instead of calculating in this integral in this coordinate, it's again it's convenient to transform this element sorry, to the natural coordinate of zeta and eta and try to calculate this integral sorry, over this line segment. Yeah. Therefore, I just wrote the same equation. Yeah, wrote the same equation, and because we are trying to calculate the boundary integral for such an element, and because only this edge are located at the boundary, instead of calculating over all of this edge, we need to calculate only over this counter from 1 to 2. And it is easy to show that DL, that is line segment here, if we transfer it to the natural coordinate, this DL should be L12 times 2 d zeta. And this L12 is nothing but the length of this line. We can easily show it. We say that, okay, any coordinate, yeah, any coordinate on this element, especially the coordinate that are located at the node number 1 and node number 2, yeah, can be calculated using this equation. Why? Eta here is 0, because when we map this triangle to this coordinate, you see that the shape function here, we have only shape function 1 and shape function 2, and for shape function 1 and shape function 2, the eta is 0 on this counter. Yeah. Therefore, x should be x1 position at the position of triangle, this node at xy coordinate times to the psi 1 zeta and 0 plus x2 times to the psi 2 zeta and 0. We can write the same equation for the y, yeah, and if I substitute psi 1 here by considering that the eta here is 0, yeah, and psi 2 by considering that again eta is 0 but psi 2 is just zeta, and again I just substitute psi 1 here and here, and after simplification and writing the common term, that is we have a zeta here and we have a constant term here, we can get these equations simply. And from this we see that dx is indeed x2 y bar times to the d zeta, and dy is y2 bar times to the zeta. And we know that this dl should be a square of dx squared plus dy squared in Cartesian coordinate. And if I substitute dx and dy from here, we have a common term of d zeta that goes out of the square root, and we have x21 square plus y21 square. And this is what? This is indeed length of this line segment again in Cartesian coordinate, and x21 is nothing, just x2 minus x1, and y21 is nothing but y2 minus y1, and it gives us the length of these edges, that is L12. Yeah. Therefore, I substitute this this dl to the line integral, to this line integral that we derived, and now we substitute psi 1 in calculation of b1 here, psi 1 here, psi 2 here, and psi 3 here. But now we are calculating this integral not in the xy coordinate but in the zeta eta coordinate, and all we need is to choose the limits of integral to be changes from 0 to 1. Yeah. Therefore now by substituting psi 1, that is 1 minus zeta, by considering that eta is 0 here, and here, psi1 here, psi2 here, and psi3 is 0 over this counter, yeah, obviously. And Q is a constant, L12 is a constant, it goes out, and V1 and V2 and V3 all is constant, and if you can calculate this integral, you will get these 4 terms. This first term comes from this, and we have a V1 with this coefficient, V2 with this coefficient, and 0 for the V3, because the third shape function over this counter is 0. And now what we have? We have a B vector, and this B vector contains coefficient of V1, V2, V3. I again remind that this boundary integral is calculated when we are dealing with Neumann or Dirichlet boundary condition, Neumann or mixed boundary condition, not Dirichlet boundary condition. Therefore, we have some unknown coefficient at the right hand side, and we need to send it this coefficient to the left hand side of the system of equation. And if you imagine, this is indeed the matrix representation of the same system of equation. Now what we need to do is that sends these terms, these 3 terms, to the left hand side of equation. And if we do this, send these terms to the left hand side of equation, we need to modify M11, M12 and M13 like this. M11 should be modified M11 minus this term, M12 should be modified M12 minus this term, and because this is plus, when it goes to the left hand side it will become minus. And because there is no coefficient for the V3, because it is not located on the boundary, therefore we do not modify these terms. And this equation all are related to the first node, node number 1. And if we try to calculate B2, contribution of the node number 2 to this, let's say, line integral, all I need, just substitute 2 instead of psi, instead of I here. Yeah, therefore we have psi2, and again the same term. And again, by substitution of psi2 at the zeta as 0, that is just zeta, and the psi1 again 1 minus zeta, psi2 that is just zeta. I think this term is extra and this is a misprinting. I mean, it is a typo. And here psi3 is again 0. Yeah, and if we calculate this integral, yeah, we can have this 4 terms, 0 coefficient for the V3, this coefficient for the V2, and this coefficient for the V1. Again, we know that this equation are associated to the grid number 2, node number 2. Yeah. And in the calculation of B2, we achieved some coefficients, that some terms that have V1, V2, and V3, and again this is unknown. Therefore, we need to send it to the left hand side, the same rule that we discussed, and we modified M21, M23, M22, and M23 according to these relations. And it is obvious that because if we calculate B3, because psi3 over this counter is 0, yeah, remember the geometrical representation, psi3 here is 0, therefore all of these terms should be 0, and we do not have any value for the B3, and we do not need to modify the matrix element of M31, M32, and M33. But remember that this is based on, let's say, based on our numbering. If we number this element like that, like following that, this is 1, this is 2, and this is 3, in this case, we need to calculate from 3 to 1. And from 3 to 1 means that we need to calculate from this path. When we calculate from this path, in this case, psi2 is 0. Yeah. Therefore, after calculation, we need to modify these terms and this term, but not these terms. Just keep it in your mind. And this is what we found for the B after transferring these extra terms to the left hand side of the system of equations. We calculate the matrix M for one element. We calculate the vector S for one element, any typical element, and we calculate the vector B again for any typical element in the case of Neumann boundary condition or mixed boundary condition, and we say that in that case we need to modify the matrix element. Now that we have all of this, we know that we have a linear system of equation and we can easily solve it. Yeah, but this is only for one element. In one dimension, we say that we can derive exactly the same equations for all the other elements. It means that we do not mark any element. We just need to be careful about whether this element are located at the edge or at the inside. In that case, we need to be careful. Should we calculate the boundary integral or not? Otherwise, everything is the same. And we can derive, indeed, we derive this matrix and this vector for any typical element, and we know that the location of the element. Yeah, we know the coordinates of the element, and this matrix is a function of coordinate of the elements and the area of the elements. In one dimension, we manually connected these elements to each other and made a big matrix. We call that matrix M. Now, but let's call this a small matrix. Let's say this matrix for an individual element with M, and we know that if we indeed assemble the total matrix, the whole matrix, that is based on the number of elements and the connectivity, we finally have some K matrix times to the V, and this V are in the coefficient, unknown coefficient at all nodes, and we have some right hand side matrix. Therefore easily we can calculate this V vector, yeah, just by calculating of the inverse of this general matrix times to the right hand side. But as I mentioned, in one dimension, connectivity of the elements was simple because we are on the line and we know that right element of each typical element is connected to the, let's say, right node of a typical element is connected to the left node of its, for example, neighboring. Yeah, but in two dimension, we need to somehow save the information of the connectivity of the elements to some two-dimensional array. Imagine we have such a coordinate, we have such a simulation area, and we discretize this area using of 6 elements. And as you see, we have only 8 nodes. For 6 elements, we have only 8 nodes. But how they are connected, you can write a table like here. And you see that here it is written number of element number 1, 2, 3 up to 6. And here we have local node number. Local node number, it means that for all the triangular elements we have node number 1, 2, 3, 1, 2, 3, 1, 2, 3 for all of them. And we have some global node number. And you see that these are indeed our global node numbers. And you see that for the element number 1, the local node number I1, what is the global node number? It is 1. And the global node number for the second node of element 1, it is 8. Global node number of third 1, 2, 3. Global node number of let's say third node of element 1, it is 2. Yeah, simply you can see it in this table. It means that we need to save this connectivity information into some two-dimensional array that here I call it with N. That first index in this array shows the element number, the second index shows the local node number, and we assign global node number to this N. Then we can use this connectivity information and assemble the matrix. And as you see, this is element number, this is local node number, and this is global node number. And for example, when you want to call some node, N here stands for the node. What is the number of node? What is N? N depends on the element number and the local node number. For example, we say that what is the node number of fifth element and the first local node number. Fifth element, first local node number is this one, therefore it is 8. Or what is the global node number of third element and the nodes, the third local node? Where is the third element? This is the third element, and the third local node here is 3. Yeah, you can see, and you see this connectivity is true for this geometry. Therefore, connectivity information is derived based on the geometry and based on the discretization, how these elements are connected to each other. We need to somehow find it and save it to some array. Then we will recall from this array the number of modes, and we will use in assembling of the matrix. Now, in practice, if we want to simulate such a we want to numerically calculate Poisson equation with the Dirichlet boundary condition that we discussed, we need to discretize this rectangle. For discretization, let's do it manually, and for manual discretization, I can divide it, for example, at x direction into 3 blocks, and at y direction, again, I can divide it into 3 blocks. And if I divide any block with such a line, I have created indeed elements, and this is element number 1, 2, 3, 4, 5, 6, so on and so forth. And you see that we have 18 elements, and now we need to have also the nodes, and let's do following. This is node now global nodes. Node number 1, node number 2, 3, 4, 5, 6, 7, so on and so forth up to 16. Therefore, here we see the global nodes number. For example, if for example consider the node element number 9, for example, and we see that this is local node number of 1, 2, 3, and we easily see that the global node number of third node of the element 9 is 10, and this is how you need to create this connectivity information. And this I defined these boundaries with A, this boundary with B, this boundary with C, and this boundary with D, and we will use this these lines in assigning of the known Dirichlet boundary condition to this node. You can find it in the code. And once we did it, we can calculate, and we assemble the global K matrix. We can calculate the potential over these nodes. Now what we have, we calculate the potential, but this is only a vector. In one dimension, the same vector was the representation of the potential at the x or y. Yeah, because we were in one dimension. Yeah, and in one dimension, this vector was the same at the x or y direction. But now we are in 2 dimension, and we calculate a vector v. Now we need to do some post-processing calculation. We need to map this vector v into 2 dimensions. And we know that this relation that we calculated indeed this, let's say this coefficient. Yeah, we calculated this coefficient. And here should be indeed the number of nodes. When we have the number of nodes 60, we have 16 elements, but shape function are 1, 2, or 3. Yeah, just do not confuse this coefficient and let's say this index and this index. But another thing that we need to consider is that we calculated the shape function in eta zeta coordinate, in the natural coordinate, but we need to, for mapping, we need to calculate shape function at xy coordinate. And for calculation of shape function at the xy coordinate, all we need to write eta and zeta as an explicit function of x and y. We have the mapping relation. I just sent this constant x1 and y1 to the left hand side. Yeah, and in the matrix representation of this equation can be written like this simply. And if you have an explicit dependence of the zeta and eta to the x and y, all we need is to calculate the inverse of this matrix and multiply it to this vector. Yeah, therefore we have the inverse of this matrix, that is 1 over determinant of matrix, yeah, times to this matrix and times to the this vector. And you see that we have explicit relation of zeta, that is a function of x and y. This multiplication to this gives us this term, and this multiplication to this gives this term, and this is nothing but again 2 times of area of the elements. Therefore, what we did, we derived the shape functions, we use triangular mesh, we calculate the matrix M, vector S, and vector B that are in the left hand side, source term, and the boundary integral. yeah, and we calculated the v. Then we say that this is a vector, and we need to map this vector to the two-dimension. And for mapping, we need to have shape functions at the xy coordinate, and we did it. All we need is just put zeta and eta in the shape functions, and we have the shape functions in new coordinate, and obviously shape functions for each element is different in xy coordinate. I think that's it. What we discussed, the code for this discussion exists in the, as I mentioned at the beginning of the video, the code exists in my Telegram channel. I put the link in the description. Therefore, please look at that code, download it, and try to resolve it for yourself, how this theory is connected to the which part of the code. If everything is clear, then it is fine. We are happy. But if you think some part is not very obvious, we can have a practice, and we can have another video, and we can discuss about that code. All I need is just please let me have your feedback in the comments. And if you have enjoyed the video, do not forget to like it, subscribe to the channel, and share it with your friends, therefore more people can see it. Thanks for your watching, and goodbye.